Here is my second lab. The hypothesis for this lab is that an object with a force on it will have an acceleration due to the force of gravity. Not only that, drag will alter the trajectory of the object slightly, leading to a theoretical terminal velocity. The concepts included in this lab were Newton's first and second law and drag, friction, and air resistance. The physical properties included would be the force of gravity equals mass times acceleration, and drag force can be calculated through negative b, which is a constant, which drags constant, times v squared, and the position and velocity update formulas. So some of the initial tracker setup information was that the video was filmed at 30 frames per second. For the scale, I used my height, which is 1.828 meters, to scale everything accordingly. The mass of the object dropped, which was a headphone case, was 3.2 times 10 to the negative 2 kilograms. And the assigned axis was that the origin was defined at the center of the headphone case on the first frame. Here is the video. So here are some of the data and measurements. The initial position vector and velocity vectors were both 0. And the object was dropped for the observational time interval was from 0 seconds to 0.566 seconds, and the object was dropped a total of 1.57 meters from the origin. So here is the code that was shown. So if you look here, delta t, the time step was 0.033 seconds, and g was defined as 9.8 meters per second squared. All right, here is the model that creates the code that creates the model. Here's the code that creates the model with drag. As you can see, drag is calculated. The drag vector is calculated by b, which is a constant that we found through trial and error, which was 0.0025 times the velocity squared. So the y velocity squared, and this was added with the weight force vector to give you force net. So the similarities and differences between the two graphs was that the similarities is that they both graphs have a parabolic shape, which indicates that gravity is affecting both. Gravity is the force affecting both, but the difference is that the obtained position, like the actual position graph, has a more accurate constant of drag constant, so it falls a lot slower than the two predicted. Even when we try to incorporate our own drag, it's not perfect. And here's an image with the model with drag. This is an image showing the sum of the forces on the object. So what does this mean? So out of the two models, the model with drag predicts a terminal velocity in that when the force as velocity increases, the force net is going to eventually equal 0 where terminal velocity occurs, because the velocity will be constant. So if the object was initially thrown downward, the terminal velocity would still stay the same, because terminal velocity is not affected by its initial velocity. It's affected by the velocity at the end. Thank you. That is the end of my presentation.